Welcome to Part 4 of this week's online lecture. In Part 4 we will discuss the vibration of ammonia, which belongs to a point group with degenerate irreducible representations. Before continuing, we need to discuss degenerate representations, and the simplest point group with which to discuss this is C3V, and so we will illustrate this with the ammonia molecule. In the C3V point group, there exists an irreducible representation E with a character for the identity symmetry operator of 2. We can see that X and Y transform like this degenerate irreducible representation. In fact, the brackets around the X and Y indicate that we must treat this degenerate basis set together. As we need two basis functions to describe this representation, the character of 2 under the identity makes sense. But what about the character under other symmetry operations? The effect of C3 on X is not just to change its sign or to turn it into something else entirely. It gets changed into a linear combination of X and Y, so we have to take them together. This is the reason why the X and Y are in brackets. They're considered to be a degenerate basis set. If we consider the clockwise C3 rotation axis, we can determine the effect on the basis set X and Y. This is most easily done by considering X and Y in cylindrical coordinates. The effect on the vector X and Y is for it to multiply on the transformation matrix given. The character is the trace of this matrix, that is, minus a half plus minus a half is equal to minus 1. With the character under each of the symmetry operations identified of this degenerate irreducible representation, let's consider a molecule with C3V symmetry. For example, ammonia. Once again, we need to identify internal coordinates in order to identify the normal modes. With 4 atoms, we need 6 internal coordinates. The geometry of ammonia can be characterized by the 3 NH distances, or bond lengths, and the 3 HNH angles. These can be used as vibrational coordinates, although it is more convenient, of course, to use the displacements from equilibrium. That is, dI is equal to Ri minus Re, and epsilon I is equal to theta I minus theta E. Let's start with the stretching coordinates delta 1, delta 2 and delta 3. The procedure is as follows. First, find the character. To do this, we add 1 for each coordinate that is left unchanged, minus 1 if there is a change of sign, and 0 for each coordinate changed into a different one. More accurately, if the coordinate stays at its origin, then the character is equal to cos theta, where theta is the angle by which the symmetry operator rotates the coordinate. Under the identity, all 3 coordinates are left unchanged, and so each contribute plus 1 to the character. Thus the character of the basis delta 1, delta 2, delta 3 under the identity is plus 3. Under the C3 rotational axes, each coordinate is changed into a different coordinate. For instance, for the anticlockwise C3 axis, delta 1 is transformed into delta 3, and delta 2 is transformed into delta 1, and delta 3 is transformed into delta 2, assuming that the displacements are labelled clockwise. And so the contribution from each is 0, and so the overall character under C3 is 0. Under the 3 sigma v mirror planes, one coordinate is left unchanged, as the coordinate is in the mirror plane, whereas the other coordinates are transformed into one another. Thus, overall, the character under the sigma v mirror planes is plus 1. Next, we need to apply the reduction formula. It is more conveniently written as the sum over classes, but then we need to multiply the term for each class by the number of symmetry elements in the class. In the C3V point group, there are 6 symmetry operations, but 3 classes, that is, the identity, the rotational axes, and the mirror planes. The number of A1 symmetries is equal to 1/6 times the sum of 1, which is the number of symmetry elements in the identity class, times 1, which is the character of A1 for the identity, times 3, which is the character of our representation for the identity, plus 2, which is the number of symmetry elements in the rotational class, times 1, which is the character of A1 for the rotational class, times 0, which is our character for our representation of the rotational class, plus 3, which is the number of symmetry elements in the mirror plane class, times 1, which is the character of A1 for the mirror plane class, times 1, which is the character of our representation for the mirror plane. Overall, this sums to 1. So there is one linear combination of delta 1, delta 2 and delta 3 with A1 symmetry. Similar analysis can be done for the other irreducible representations. This reveals that no linear combination exists with A2 symmetry, but one linear combination exists with E symmetry. Note that the overall dimensionality has been maintained. There are 3 coordinates in the basis set to describe the 3 stretching vibrations. There are 2 linear combinations of these basis functions, but the one with E symmetry is doubly degenerate, and so overall we have maintained our 3 vibrations. Finally, we can apply the projection formula to find the form of the vibrations. We have to sum over all the operations. It cannot be simplified to a sum over classes. Note that the dimension of the irreducible representation, L sub gamma, can change in the C3V point group. We do not need to project with A2 symmetry because a linear combination with that symmetry does not exist. If we project out the combination with A1 symmetry, this is done by applying the PA1 operator on delta 1, although any coordinate would result in the same answer. The result is 1/6 times the sum of 1, which is the character of A1 for the identity, times the identity operator on delta 1, plus 1, which is the character of A1 under the C3 rotational operator, times the C3 rotational axis operator on delta 1, plus 1, which is the character of A1 under the C3 squared rotational operator, times the C3 squared rotational operator on delta 1, plus 1, which is the character of A1 under the sigma A mirror plane, times the sigma A mirror plane operator on delta 1, plus 1, which is the character of A1 under the sigma B mirror plane, times the sigma B mirror plane on delta 1, plus 1, which is the character of A1 under the sigma C mirror plane, times the sigma C mirror plane on delta 1. Overall, this results in a linear combination that is 1/3 delta 1 plus delta 2 plus delta 3. This is the symmetric breathing mode. From this, we see that the A1 vibration is the symmetric breathing mode. The projection formula, however, only gives one component of the E vibration. It gives 2 delta 1 minus delta 2 minus delta 3. But this does indicate that it is an asymmetric stretch. The other component is proportional to delta 2 minus delta 3, as this is orthogonal to the vibration identified. In the same way, the bending vibrations can be described in terms of the 3 coordinates epsilon 1, epsilon 2 and epsilon 3. We get a symmetric bend, epsilon 1 plus epsilon 2 plus epsilon 3, symmetry A1, and a pair of asymmetric bends, 2 epsilon 1 minus epsilon 2 minus epsilon 3 and epsilon 2 minus epsilon 3. These have symmetry E. It should be noted that for a nonlinear tetraatomic molecule like ammonia, we should have 6 vibrations in total, and we have indeed identified 6 vibrations. However, we are able to separate the vibrations into stretching vibrations and bending vibrations. How do we know how many stretching vibrations there are? Well, there is always the same number of stretching vibrations as bonds in the molecule, as stretching vibrations are solely to do with the displacement of atoms along the direction of bonds. The remaining vibrations can then be classified as bending vibrations. Because the asymmetric stretches are components of the same degenerate representations, they are guaranteed by symmetry to have the same frequency, even though they look significantly different. This is the end of part 4 of this week's online lecture. Please continue on to part 5.